when we do know what sigma is, because honestly, in real life, you never know what. If you don't know what your population mean is, you're not going to know what your population standard deviation is. It doesn't make any sense. So we're only going to deal with spots where we don't know what the population standard deviation is, because we don't know the population mean. So when you don't know that, we talked about this a little bit in class, but if I don't know what is going on? If I don't know what mu is, what's my best guess for mu? If I don't know mu. Mu is my population mean. What would I use instead? It's my best guess. If I don't know my population mean. Anyone?
Sample mean.
Yeah, my sample mean. Right, in other words, if I don't know the average age of the entire world, the best thing to do is to take a sample of everybody, of a handful of people in the world, and use that sample mean to guess what the whole population is, what the whole world is. So if you don't know the population mean, you take a sample and use the sample mean. So if I don't know the population standard deviation, what should I use instead, do you think? Someone else? Anyone else? If I don't know my population standard deviation, what should I use instead? Unmute yourself. Give me an answer, someone. Or else I'll start calling on people.
Sample standard deviation.
Yes, sample standard deviation. So you're going to use S. These are both standard deviations. This is for the population. This is for a sample. The catch is that because my S is from a sample, it's not going to be perfect. It's going to be off a little bit. So instead of using the Z distribution, the Z table, we're going to use a T distribution and T table instead. So we're going to talk about that in just a minute. But typically what we would use for our standard deviation would be, you guys remember from central limit theorem, it would be S over square root of N. Sorry. It would be, normally it would be sigma over square root of N. Right, that was that whole central limit theorem, all those 25 games from Steph Curry. Right, so instead we're going to use S over square root of N. But because, again, S is not perfect, we got to use a little bit larger number for our critical value. So instead of using the Z table, we're going to use the T table. Okay. So here's the T table and how to use it. The top part is going to be your confidence intervals, or your one-tailed or your two-tailed hypothesis test. So this upper part here, you just kind of slide along and figure out, it helps you figure out what column to use based upon what confidence interval you're using. Over here, this is your degrees of freedom. Degrees of freedom is n minus 1. So degrees of freedom equals n minus 1. You guys need to know that. It's super important. df equals n minus 1. Absolutely have to know that. You're going to be in serious trouble without that. So that's where you find degrees of freedom. And then slide down. So if my n is 22, my degrees of freedom is what? If n is 22, what's my degrees of freedom, everybody?
21.
Yep, 22 minus 1, 21. So slide down to 21. That's the row you want. If I want a 95% confidence interval, I'll slide down that and I'll grab 2.080. So here is the T table over here on the right. I want you guys to go ahead and fill out this part, find these numbers using the T table. So you should all have this handout. I'll move this over a little bit so you can see it. And this is the T table. This will give you all the numbers you need. So I'm going to give you guys 2 minutes to use this T table. Again, it's a confidence interval. So find a confidence interval that you want. This is 95%. Figure out your degrees of freedom. So when n is 2, when n is 11, n is 61, and n is 121, find the T-score for those. 2 minutes. Go ahead. So let's get back to where we were. So here we've got n is 2. When n is 2, what's my degrees of freedom?
1.
Yeah, so degrees of freedom again is equal to n minus 1. So that would be 1. 2 minus 1. Everybody on board with that part? So when n is 2, my degrees of freedom is 1. So I'm going to use this row right here, confidence interval 95%. So I'm going to use this column here, degrees of freedom 1. It's going to be right there, 12.706. So that'll be my answer here, 12.706. There we go. When n is 11, my degrees of freedom is what? 10, yep. Again, n minus 1. So we're going to look up that one. Degrees of freedom is 10. 95% confidence interval, so it's going to be right here. 2.228. This is terrible. 2.228, and then when n is 61, so if we kind of slide over to our sheet over here, I don't know if we can do that. Oh yeah, we can. N is 61, my degrees of freedom is 60, so that would be this guy right here, 2.00. Everybody good with, everybody with us? And then when n is 121, my degrees of freedom is 120, so it would be 1.98. Generally speaking, I want you guys to round down. So if you got something that was like 80 or even 100, I prefer you guys round down to 60 because you really don't have enough to say 120. So that should, so 100 should round down. Or if you had like say 250, that should be rounded down to 120, if that makes any sense. Are you guys kind of following what I'm saying? And then the last one was the z-score. The z-score is the very bottom row where it says infinity. So there should be a row down below, which it doesn't show up on here because I cut it off too soon. But the infinity row would be my z-score, which is 1.96. So that's the beauty of this, is that this t-table, the very bottom row of it, is your z-table. It's your z-scores. So this whole thing now replaces your that chapter 7 thing that we had before. It replaces this guy here, this table here. That's the bottom row of this t-table. So you can just use that instead, because you can use this t-table on the exam. So you'll kind of, if you look through this, you'll notice that 12.706, go ahead and use that instead. You kind of see as it kind of goes through, when n is small, it's really huge. And as n gets larger and larger, then it becomes, when n is 11, it becomes a lot smaller, 2.228. When n gets even bigger, 61, it becomes 2.0, which is really pretty darn close to 1.96. And then n is 121, it gets even closer. And eventually, as n gets bigger and bigger, it becomes 1.96, when n is infinity, kind of. So what this is saying is that your estimate for S is really bad when you're only talking about a sample size of 2. But as your sample size gets bigger and bigger, your S, your sample standard deviation, gets better and better. So the t-score that goes with it, the critical value that goes with it, can get closer and closer to the real critical value, the z-score of what it should be, 1.96 in a perfect world. So that's kind of how all that works. So, whoa, move that over. All right, so margin of error, it's pretty similar to the last thing. Your error is equal to your critical value, whatever that is from your table, in this case from the t-table, multiplied by the standard deviation for a sample, s over square root of n. And again, where your critical value, you're using n minus 1 degrees of freedom. And then to find the actual confidence interval itself, you take your best guess, your best point estimate, x bar, and you do plus or minus your e. Right, so your lower limit is going to be x bar minus your e, your upper limit is going to be x bar plus your e. and you can either put them in parentheses with a comma between them, or you can put the lower limit and the upper limit and put, that mu is greater than the lower limit and less than the upper limit. So you can do it right either way, it doesn't matter. Here are a couple comments on how to find it. Let's get a reader. Let's see, Allie's thing is broken. I can't, oops, oh no, what happened? Oh, that's bad. Ulysses, can you read it for me?
Yeah.
Thanks.
Procedures for constructing a confidence interval for the mean with or unknown. Verify that the sample is either normally distributed or n is greater than 30. Using n-1 degrees of freedom, use a table to find the critical value, CV, for the desired confidence level and whatnot.
Good. Keep going.
Evaluate the margin of error. E equals CV over S, square root of n. Find the values of the x mean minus E and
X bar,
x
X
mean
bar.
plus B.
Okay, X mean,
X
yeah.
bar.
Yeah, X bar, right. Good.
Substitute those values in those general format for the confidence interval.
Good.
X bar minus E less than or greater to the mean, U, to that of X bar plus E. Round the resulting confidence interval limits to 3 sig fig.
Good. Right, so the mean is greater than that and less than this. Perfect. So that's your basic standard playbook for this one. So this is what you guys got from yours. So sample of 14. What's 14? Sample of. So 14 is my what, guys?
Sample size.
Yep, my sample size, my n. Great. So the average of this, so this is the average of the sample. So the average of the sample was 33.2. That's my X bar, my sample mean. And the standard deviation was 8.3, that's my S. So here my n is 14. Right. And then my degrees of freedom is n minus 1, right? So that's 14 minus 1, or 13. And then my X bar is, we said that was 33.2. And my S was 8.3. So then when we go ahead and do our E, we can say that E is equal to our critical value. So if you pop over to our table, well, let me figure out what critical value is first. Our critical value, if you hop over to our table, let's see, 13 is our, oh, I moved this, I gotta move this over. Oh no, okay, let me undo this, hold on. Let's see. It's 13 and 95% confidence interval, so it looks like it's 2.160. So my critical value is going to be 2.160. And so now we need to find the error. Move this up a little bit. All right, so our error will be our critical value, 2.160, times, I'll leave a giant parentheses here so we have some room for this. The top part is going to be S, 8.3, over square root of n, which is going to be 14. Just move these guys around so we can see them a little better. So much easier when I can actually write on this. This is kind of super annoying. over square root of 14. So what did you guys get for E? Anybody?
4.791.
4.791. Yep. Great. And then remember, our interval is going to be x bar plus E, x bar minus E, comma, x bar plus E in parentheses. So we're going to have, what's our x bar 33? Our best guess minus 4 point, we'll round it 4.8, and 33.2 plus 4.8, which ends up being 28.6, is that right? 28.4, comma, 38.0, looks like. All right, you guys have questions about this one?
The x bar minus E and x bar plus E, that represents what?
That represents our confidence interval. So x bar, so remember, x bar is our best guess. So if you kind of look at it, my best guess is x bar right here. And I want to take, but the odds of that being perfectly correct, this one guess, is pretty slim. So instead I'm going to take an interval around it. I'm going to go kind of a little bit this way and a little bit that way so that I have this range. So I'm going to take my x bar, I'm going to add, let's see, which direction is it? I'm going to subtract E, and I'm going to add E so that this is sort of my lower limit and my upper limit. Do you guys remember before with that whole unusual, usual values, we take our best guess and we subtract 2 standard deviations and we add 2 standard deviations, and that would be our upper and lower, lower likely, usual value or upper usual value. It's similar to that. Only in this case, we're going to be going, it looks like 2.16 standard deviations this way and 2.16 standard deviations that way. So that's how we got to these numbers here. We took our best guess, 33.2, and we subtracted 2.16 standard deviations. This is a standard deviation. This is how many standard deviations we want to go. Our critical value times the standard deviation. So I'm kind of thinking now is a good time to take a little break. Actually, let me do 2 more things real quick. Let's go ahead and do those. So the first one is, again, talking about finding the point estimate and E from the confidence interval. So we did this before. We did this with proportions before. Remember, you have, here's your x bar. It's right down, smack dab in the middle. And then from the x bar, I added E, right, to get my upper limit. This is my plus E. That's my upper limit. And I subtracted E, oops, kind of a weird, sorry, to get my lower limit. So that means that I can find, if I have my lower limit and my upper limit, if I have a confidence interval, the lower limit, comma, the upper limit, I can find x bar. Why? Because x bar is smack dab in the middle of them. All I have to do is take these 2 things and average them. In other words, I add them up and divide by 2 because there's 2 of them. And that's how I find my x bar. I can also find my error because from here to here, it's 1 error, 2 errors. It's 2 errors to jump from here to here. So this distance from here, from my lower limit to my upper limit, is 2 errors. So if I find that distance, subtract them, and divide by 2, I'll get what an error is. So that's pretty straightforward. It's just like we did with proportions. in our last lecture of the semester that we had before break. And the last thing I wanted to go over was this part here, kind of just a quick summary of them, picking out the appropriate distributions. So again, remember, we are not going to use the mean when we know sigma, because that's ridiculous. It never happens. Instead, we're going to deal with the means. These are means. Let me use a different pen. These are means when we don't know what sigma is. In other words, we're going to have to approximate using S. So for this one, that's when we have an X bar, we have a mean, a sample mean, and we're trying to guess what the population mean is. This is going to use a T distribution. How do you remember that? Just think of mean Mr. T. Mr. T, he's not mean, but he looks mean. Right, so because Mr. T looks mean, just remember mean Mr. T, and that'll remind you, so when you see a mean, use the T distribution. Mean T, mean Mr. T. Then we have our proportion. So for proportion, I'm just going to write this out because I can't do that very well. Proportion, for this one, this is when we have a p-hat, a proportion, and we're trying to guess at what our population proportion is, what our regular p is. And that's going to use just a regular z distribution like we've been using in the beginning. And the way you remember that one of my students said, well, just think of easy peasy, right? You guys have all heard easy peasy. Proportion, p, uses z distribution. Z, so easy, p, z, proportion, z table. So pz. So it's just those are just mnemonics to help you remember. So mean Mr. T, easy peasy. Everybody just say that once. Say it to yourselves. Mean Mr. T, easy peasy. Go ahead, say it.
Mean Mr. T, easy peasy.
Good. Excellent. So let's go and take a quick break, and we'll come back in 10 minutes, 6:16, and we'll start back. So take a quick break, walk around a little bit, okay? If you go to Canvas, and you go down to video playlists. Oh, I guess I should put this one in there. Oh yeah, no, video playlists for lectures chapters 7 through 9. Then it'll come in here. So here's 7.1, here's 7.3, and then I'll put 8.1 in there after that. And those will be the links to the playlist. And the playlist will take you to the YouTube site that has all the 3 or 4 videos for that lecture.
Got it. Thank you.
You're welcome. And then, yep, here are the handouts and notes and everything.